channel. Today we'll be learning about the Krebs cycle. Yeah, a fun cycle to learn about, a fun pathway to look into. Now the Krebs cycle is also called the TCA cycle, tricarboxylic acid cycle, and it's what we want to dive into today. Now, earlier we established that usually glucose is converted to pyruvate by a process called glycolysis, and this happens within the cytosol. Now, from the cytosol, pyruvate is carried into the mitochondria in the presence of oxygen to be converted to acetyl-CoA. The acetyl-CoA thus formed is now carried into this cycle we call the Krebs cycle. It's called tricarboxylic cycle, TCA cycle, citric acid cycle, different names. It has different names. Now, what is important about this cycle? The site, it happens within the mitochondria. It happens only in the presence of oxygen. Now, what again should we note about this cycle? This cycle is regarded as an amphibolic pathway, amphibolic cycle. Amphi. Anytime we hear the word amphi, it means when it's two-sided. So, for example, we hear of amphipathic. Amphipathic is when you like water at the same time you hate water. So I have a particular molecule that a part of it likes water, a part of it hates water. Likewise, when you hear amphi, anytime you hear amphi, it's always the idea of two sides. So when I hear amphibolic, so I'm saying that the Krebs cycle is amphibolic in that it involves building up, that is anabolic process, and catabolic. Now, what is the building up? First, it starts off, glycolysis begins with acetyl-CoA. Of course, I mentioned it's within the mitochondria, joining with oxaloacetate. Then oxaloacetate is 4 carbon, acetyl-CoA is 2 carbon. You realize they join to form someone, just one person. And that one person is citrate, who is 6 carbon. So you can agree with me that this is actually an anabolic process whereby I'm forming something. But following the formation of citrate, which is 6 carbon, every other part is actually breaking down to go back to form a 4 carbon person. So it is amphibolic because it has both building up, anabolic, and then breaking down, which is catabolic. Alright, so I mentioned happens with mitochondria. Now the preliminary step for this is when pyruvate is changed to acetyl-CoA. We did that earlier when we did the fate of pyruvate. I just concluded topic. So now let's look up. Now from here, citric acid is changed to isocitrate. Usually this is an isomerization process, so it is reversible. It is an isomerization process. Now the first one was irreversible. Now after I form isocitrate is converted to give me alpha keto glutarate. I will expand the pathway as we go on, but I want us to have a rough sketch. This was 6 carbon, this is still 6 carbon. But this particular guy you see here is 5 carbon. Now, why would I change from 6 to 5? One of the key things you should take note of here is that for me to change from 6 to 5, we mentioned it last time, that change in carbon, at number of carbon atom in a sugar is either by addition of CO2 or removal of CO2. In this case, 6 to 5, that means I am removing CO2. And this is also irreversible. I move from here, we go to alpha. We go to succinyl-CoA. Now you can see carefully, this is a 4 carbon guy. Moving from 5 to 4, you get it right. What am I losing? I'm losing CO2. But I'm having CoA here. I did not have him before. That means I've added CoA ash. I established this in our last video. Please, I just concluded video that was on the fate of pyruvate. What happens to pyruvate? We established that CoA is actually coenzyme A, and the idea of ash SHJ is the specific part of CoA the active site is actually on the sulfur found in the coenzyme A. So we continue from succinyl-CoA, we move to succinate. And usually you see I had a CoA, there's no CoA, that means CoAsh has gone out. Then from succinyl-CoA we change to fumarate. Then from fumarate we change to malate. And from malate we go back to oxaloacetate. Every single one of these guys are actually 4 carbon. So I have 6 carbon citrates change to 6 carbon citrate. There is no loss, so that's just isomerization. Iso. So I change. Usually it involves removal of water and re-addition of water. There is an intermediate we call cis aconitate. An intermediate we call cis aconitate. So in between two of them, we have intermediate called cis aconitate. Now likewise, when I come in here between isocitrate and alpha keto, I also have an intermediate we call oxalosuccinate, but I will come back to that later on. Then from 6 I changed to 5, alpha ketoglutarate. From 5 you change to succinyl CoA 4. That means you have lost CO2 again. But look at the key thing here, I've added CoAsh. Now why? That's how I have my CoA. Now for me to move from someone and change to another 4, there is no loss of CO2, there is no gain. So rather, what am I doing here? Changing from 4 to 4, nothing has to do with carbon. Rather, CoA has left, so CoAsh. Right here, succinate becomes fumarate, fumarate becomes malate, and malate becomes oxaloacetate. Oxaloacetate is now used for the next Krebs cycle. Like I earlier mentioned, something we'll mention later when we do anaplerotic reactions and cataplerotic reactions. Constantly, as I keep doing this pathway, people are being used up. So the lower I use this people, as I keep doing this pathway, these people are used up, and then the formation of anybody that is being used up here will affect reformation of oxaloacetate. So oxaloacetate, as it decreases, we have some reactions that can replenish people in this cycle called anaplerotic reaction. So this is all about Krebs cycle. We'll just mention the enzymes. Now, please take notes. The places that are irreversible here is the first step when are the places where we have change in number of carbon atoms. So let's observe. 4 is 4, 4, 4. There's no change, so there's no irreversibility. That means all of these places are reversible. So 4 to 4 to 4 to 4, all of them are reversible. When I change from 4 to 6, it is irreversible. 6 to 6, nothing. 6 to 5, it is irreversible. 5 to 4, irreversible. 4 to 4, so this will be reversible. So that's a cheat code for it. So we have the reversible guys and the irreversible guys. So that's that. What else is important to note about Krebs cycle? The enzymes of concern and other things that happen in each of the steps. So I'll take the steps one after the other. Now I'll start with the first one, which is formation of citrates. How do I form citrates? If you can look carefully, oxaloacetate is being added to acetyl-CoA. A 4 carbon person added to 2 carbon, and the name of the enzyme in this step is called, I'll call this 1, 2, 3, 4, 5, 6, 7, and 8. Now, the name of the enzyme is for step 1. So for step 1, of course it is a cycle, we can start from anywhere. So step 1 is conversion or formation of citrates. Let's use it that way. Formation of citrate. Please, the enzyme here is citrate synthase. So it's an enzyme that synthesizes citrates. An enzyme that synthesizes citrates. And so that's the enzyme for this step. Aside from that, like I said, this step is actually irreversible. The step is irreversible. Now, what else should we know? 4 to 6. I think that's all. Nothing else to really know about this step. It's one of the regulatory steps. Remember when I taught glycolysis? If you have not watched our video on that, you check our playlist, Metabolism of Carbohydrates, you see it there. Now, when we discuss glycolysis, we established that any step that's irreversible is usually regarded as the regulatory step. And in this case, my regulatory step will be step 1, step 3, and step 4. Those are the irreversible steps. And their enzymes, step 1, like I said, is citrate synthase. So it's one of the enzymes. I go to step 2. What do I see in step 2? In step 2, citrate is changed to isocitrate. But what I would like you to see is that I'll have to write that one out. Citrate becomes isocitrate. But I said that this is actually a two-step reaction where I form cis aconitate before I go down to form isocitrate. Now the thing is, right here there's removal of water. Usually we need a cofactor ion 2+. Right here there's addition of water. I will explain why this is so. Now the idea here, let me use a template of organic chemistry. The idea here is that when I remove water from a compound, so let's say I want to use a particular, this is not exactly the way it is, but this converts what it is. Now let's say this is what I had before. 3 carbon compound where I had, let's say I had my OH here, add my H here. If I do dehydration, removal of water, look at what I will have in this compound. We have a double bonded to this, and then a carbon that is that way. So that will be my guy. But now what should happen if I come back and add water, but this time around I don't add OH to the carbon atom it was before. I choose to add OH to another carbon atom. So this is removal minus water. Now I come back to the same compound, I do plus water, but this time around I now form this. So you realize that I have moved OH. I removed water, OH and H. I removed OH from here. When I came back to add water, I did not add it in the same pattern. So that OH now enters this place. That is the guy here, and then H stays here. So this is what happens in these templates. Water is removed. In the presence of iron, the enzyme, the name of the enzyme is called aconitase. That's the enzyme name. And then it forms an intermediate called cis-aconitase. Now I go ahead again. The same enzyme aconitase, but this time around addition of water now forms isocitrate. Please remember I said this was a schematic. This is not real because like we know citrate has how many carbons? 6. So if you see the people I drew on the board had how many? 3. Okay, so I believe we have this. Now so we go ahead. So that's all about step 2. Like I said, it is reversible. It is reversible. So once this happens, you can go back. When this happens, you can go back. Alright, so from here, isocitrate, for the first step, there was really nothing to write. That's why I didn't write. Isocitrate can now be changed to alpha ketoglutarate. And this particular step called step 3, the enzyme that catalyzes this step is called isocitrate dehydrogenase. And so from the name of the enzyme, I think you can get the trick. So isocitrate dehydrogenase. From the name of the enzyme, you can get what it does. And like I said, it forms an intermediate called oxalosuccinate. Now, I don't want to write that down so it will not disrupt our work and the space. So now we see isocitrate is ultimately changing to alpha ketoglutarate, which is 5 carbon. So for me to change from 6 to 5, that means I have removed CO2. But for me to have dehydrogenase, I removed hydrogen from someone, added to another person. So that means I had required coenzyme. And the principal coenzyme we use here is NAD plus. NAD plus. You could ask me a question. Why am I keep doing NADH plus H plus? What's the nonsense there? Because when we learn about FAD, it is FADH2. It is because NAD actually has only one spot. Like it can only accept one hydrogen atom. But when we remove hydrogen, we remove them as 2. That means we'll fix one on the NAD plus to change into NADH. And then we'll have one hydrogen ion appearing freely. Okay, so that's that. So that covers step 3. The enzyme is called isocitrate dehydrogenase. And you see, it's doing 2 work. Both the dehydrogenase action and then removal of CO2, decarboxylation. So that covers step 3. We go to step 4. What happens in step 4? In the step 4 of this pathway, alpha ketoglutarate is converted to succinyl-CoA. Alpha ketoglutarate is converted to succinyl-CoA. So right here, like you see, CoA, that means there's addition of CoH. What else do I see from this? The fact that the name of the enzyme is usually called alpha ketoglutarate dehydrogenase. So from the name that I mentioned, dehydrogenase, same pattern we've learned before, we have this occurring. NAD plus is changing towards NADH plus H plus. Yes, yes, yes. Now you see here it was 5 carbon, it's changing to 4 carbon. What do you think has happened? Decarboxylation. So like we have always said, decarboxylation, only way carbon changes in a compound is by removal of CO2. So that's for that. Now, so that has covered step 1 to step 4. I established earlier that step 1, step 3, and step 4 are irreversible. For that reason, the enzyme catalyzing these steps are regarded as regulatory enzymes. So if you ask what are the regulatory enzymes of Krebs cycle, yeah, take a deep breath and tell me the enzymes. Number 1 is what? Citrate synthase, catalyzing step 1. Number 2 is what? Isocitrate dehydrogenase. Catalyzing step 3. Number 3 is what? Alpha ketoglutarate dehydrogenase. So now you see carefully, I mentioned that this irreversibility comes only when I'm changing the number of carbon atoms. That means when I move from 4, as I keep going down, there's no change in carbon atom length, and so all of them will be what? Reversible. All right, so let's go into step 5. Let's go into step 5. Now, step 5 is pretty sweet. Step 5 is pretty straightforward, sweet and straightforward. What am I saying in step 5? Step 5, succinyl-CoA is converted to what? Succinate. You can see that carefully. And from what we established so far, you know what is happening. So for me to have moved from succinyl-CoA to succinate, the only change in this place is that there have been loss of CoA. So that means CoH will go out. But a particular thing happens because this step 5 is actually a step of substrate level phosphorylation. If you watched our video on glycolysis, you would have learned that substrate level phosphorylation is actually a case whereby you realize that the substrate is used to phosphorylate ADP. So I'm transferring phosphates either directly from the substrate or from the reaction to ADP to now form ATP directly without having to go into electron transport chain. So if you're still having struggles with it, you watch our video on glycolysis, you will understand it better. Now, so from here, succinyl-CoA is converted to succinate, and I mentioned that it is a substrate level phosphorylation. But the truth of the matter here is that what we actually do is that inorganic phosphates is added to GDP to form GTP. And if you see carefully, this would have not been substrate level phosphorylation because phosphate is from the soil, it's not from this reaction added to someone to form this. But the fun is that the GTP that is formed is now what phosphorylates ADP. So that we can now have GDP back and then ATP. So this is what I want you to see. In this reaction, the smoke to the reaction, straight up, succinyl-CoA will lose CoH, becomes succinate. But while this is happening, GDP will react to PI, inorganic. So that's the opposite of Hydrogen. This was, whenever I have someone plus water, so it's the opposite of hydrolysis. So I'm actually picking them up to join, and that's condensation. I'm doing GDP plus PI to form GTP. Now, of course, water will go out. There's no need to mention that. When you now look at this, the GTP form will transfer one phosphate to ADP to form ATP. So remember, whenever I form ATP from this reaction, that is from a substrate in the reaction, the ATP or that step is always called substrate level phosphorylation. Now, we're done with step 5. Okay, the enzyme for this step, of course, you know it is reversible. The enzyme for this step is called succinate thiokinase. And earlier taught how enzymes are named. Enzymes, the naming of enzymes are very nice and direct. Like we've heard of citrate synthase because it synthesizes citrates. We go to another one, we heard of alpha ketoglutarate dehydrogenase. It acts on alpha ketoglutarate to remove hydrogen. So it's that direct pattern. But when you see something like succinate thiokinase, because we are looking at it, it's reversible, we are looking at it from this perspective. Succinate, to this succinate, we are phosphorylating him. We are joining GTP or ATP to him. So I am actually transferring phosphates to him. So that's what we are looking at. That's why we have the name kinase. Kinase are enzymes that transfer phosphates. Now, Thio here is because of sulfur in CoA. So that's that. Now we go to step 6. Step 6 is conversion of succinates to fumarates. Conversion of succinates to fumarates. It's also a reversible step, as I know you know already. Now, but the key thing about this particular step we're looking at is that the enzyme is called succinate dehydrogenase. So from a normal peak, dehydrogenase will mean I'm removing, yes, you got it right. Dehydrogenase will mean I'm removing hydrogen. But then, if I'm removing hydrogen, I'll need a coenzyme. And usually the coenzyme we think of is NAD. But for this particular step, this is the only exception. The coenzyme we use here is FAD plus, and we have FADH2. Why am I having FADH2 and not FADH? The same reason we gave before. Right here, FAD actually has two, it can accept two hydrogen ions. So he's free to accept that, and then that's why I have him in this format. So succinate dehydrogenase catalyzing this step, 4 carbon changing to another 4 carbon. Irreversible step. So that's about this step. So of course, FAD will also enter. We'll talk about electron transport chain in one of our videos shortly. Still in this series, FADH2 is now carried into electron transport chain to produce energy. Now we go to step 7. In step 7, what happens in step 7? Fumarate changes to malate. Of course, nothing much to write on. The enzyme for this step is called fumarase. Fumarase is not much to talk about this particular step. So the enzyme for this step is called fumarase, and it's removal of water. So water will go out, and then we have malate. Same 4 carbon, nothing much about it. Then step 8, which is our last step. Please, it is reversible. For step 8, which is our last step, malate is converted to oxaloacetate. When we were talking about the fate of pyruvate, we mentioned pyruvate can be converted straight to oxaloacetate by the help of an enzyme called pyruvate carboxylase. But at the same time, it can also be converted to malic acid, but it will still be heading to oxaloacetate. So first, I changed to malate and malate to OAA. So this is how it comes in. From here, I can do malate to oxaloacetate. Remember, it is also reversible, and here it is a dehydrogenase. So NAD plus changes to NADH plus H plus. So with this, we can carefully see that the name of the enzyme is called malate dehydrogenase. So that covers that for Krebs cycle. So what have we learned in summary? Krebs cycle is also called TCA cycle. Now we established that this cycle is amphibolic. That means it has two sides to it. It can both build up and it can break down. How is the build up seen? When 4 and 2 joins to form 6, that is building up something. But when I start changing from 6 back to 4, I'm breaking down. That's catabolic. Now we established that 3 of these steps are irreversible, and those steps are usually regarded as the regulatory steps, and they also have regulatory enzymes. And these steps are easily identified by just looking at any place there's change in number of carbon atoms. So from 4 to 6, 6 to 5, 5 to 4. So those are the steps of concern. Now, what else was important? We established also that during the course of this, 3 NADH are being used. During step 3, NADH is produced. NAD plus is changed to NADH. That means the dehydrogenase was at work. During step 4, NAD plus is also changed to NADH. Likewise, when I get to step 6, dehydrogenation is also happening, but this time around, the coenzyme is actually FAD plus. Then when I get to step 8, I use NAD again. So 3 NADs plus, that's 3 of them are being used up here, and then 1 FAD plus is being used up. And please remember that all of these things we are doing is for 2 pyruvates. Remember how it was 1 6 carbon breaking down to form 2 3 carbons. So the 2 3 carbons change to their own acetyl-CoA that comes in to do Krebs cycle. So that's all to know. That's all to know about Krebs cycle. Please stay tuned to this channel. Thank you very much for joining us today. We'll meet again where we'll be discussing about the energetics. How do we actually get ATP from this in our next video? Okay.